Hello, and welcome to Huffman Computer Science. The most common interface for entering data into a computer is the keyboard, and most peripheral keyboards these days incorporate the USB protocol. But there is an older port, one which came before USB and had largely been the standard as far as human interface devices go. The PS/2 port from IBM's Personal System 2. You can still find the port on some motherboards today, and even some USB keyboards still are built with the PS/2 protocol as a sort of fallback option. And while you can still buy PS/2 keyboards, both old and new, I was hit with a sudden thought. I've spent so much time working with various computing systems, even going so far as to build homebrew systems from scratch. Why not go beyond the computer and actually create the human interface device from scratch also? In particular, could I create the PS/2 keyboard from scratch, and do so using hardware which was very close to what the original keyboards would have used? Fortunately, I'm here to tell you that I did indeed successfully reverse engineer the PS/2 protocol, and in doing so, went so far as to create the rest of the keyboard from scratch also. Well, at least assembled from scratch using some discrete pre-manufactured components, a 3D printer, and even a breadboard. And in today's project video, I'll be showing you exactly how I did this, and even some of the troubles faced along the way. The microcontroller I'll be using is the AT89S52 from Atmel, or Microchip, which contains the 8051 architecture with 8052 additions. I ended up choosing this microcontroller mainly as the 8051 architecture was out and available when the PS/2 protocol first came to light. It's also very similar to what I understand is the actual microcontroller that IBM used in their original PS/2 keyboards, which is the EF6805 8-bit microcontroller. Although, to clarify, I'm only guessing that IBM used this microcontroller in their keyboards based off pictures I've seen online of Model M controller boards, and I don't have a Model M keyboard available to disassemble and verify this with myself. That said, I'm still reasonably certain an 8-bit microcontroller was behind the scenes driving the original PS/2 keyboards. And since the EF6805 unfortunately doesn't appear to be manufactured anymore, I figured I might as well choose another architecture that would have been available at the time and is currently still manufactured. And from what I read, the 8051's predecessor, the 8048, was actually used in the keyboard of an earlier IBM PC that came before the Personal System 2. So maybe it's not too far off to suggest that the 8051 isn't totally foreign to the task. The basic premise for any keyboard is the design of the key matrix. This is the arrangement of all your keys or buttons in a grid-like pattern, such that by scanning over the matrix you can determine what key is pressed based on its location in the matrix. This basically works by applying a digital high signal, or 5 volts, to a column. Then depending on which keys, if any, are pressed in that column, the key acting as a switch will switch on the row that the key is in. Then that digital high value can be read or detected on the row, and by knowing the currently active column, you can determine the exact coordinate of the key switch that is pressed on. Though one more important component in a key matrix are the diodes connected to one side of each key switch. They help to mitigate ghosting, where you may press a specific combination of keys, but end up detecting a key that isn't even pressed among them. For example, assume the diodes are not present. At this moment in time, the microcontroller is applying a digital high signal to the third column, or port 1 bit 2, as the keys with red arrows are pressed down. Current flows from port 1 bit 2 into the respective column and through the closed key switch connected to port 0 bit 2. The current proceeds into the row tied to port 0 bit 2, then through the closed key switch connected to the column tied to port 1 bit 0. Then, since the key switch connected to the row tied to port 0 bit 0 is closed, the current flows through the closed circuit and finally is observed directly on port 0 bit 0 of the microcontroller. This causes a false detection, as in this scenario the microcontroller is detecting the key switch located at column port 1 bit 2 and row port 0 bit 0 as actively pressed while the key switch is actually open. However, this issue of ghosting is prevented by placing diodes in series with each key switch. Since the diodes allow current to flow in only one direction, this backfeeding is prevented from happening, and as a result, you won't have keys on your keyboard acting spooky. Now with the principles of wiring the matrix understood, it needs to be mapped in size to service all the keys on the keyboard. I decided for this keyboard design I wanted a compact keyboard that still had the function keys present. With the layout decided, I needed to map where to wire each key in the matrix. For that, I created this simple diagram of how to map each key. The grid helps to break down how the columns and rows will look in the matrix and will later help with programming the respective positions of each key during key scanning. Notice also how some of the grid squares are empty, which you'll eventually see the code reflects in that no valid key codes are present at those locations. This was done for ease of wiring, but also can allow for quick expansion if a couple extra keys are desired to be added on to this design. With the plan made, it was time to design the keyboard body to contain the key matrix. Since I wanted this project to incorporate as much DIY as possible, and I didn't want to wait on a PCB to be manufactured, I decided on 3D printing the body and keycaps myself. I first went to Thingiverse to see if there's any suitable models I could utilize for what I envisioned. And while I didn't find the exact design I had in mind, I did find two that provided me solid bases to work with. So I went to work remixing the two STL files. I modified the body of one design to be a very minimalistic panel, adding on the escape and 12 function keys. From the other design I used only the keycaps, and created the other specially sized keys, such as the spacebar or enter keys, from the one. Which, by the way, if you decide to follow along and print these same keys, the following keys with matching colors are of the same size. Then after that, I made some simple stands and beams, which when added to the main keyboard body helped to provide rigidity and space for wiring underneath it. But once the 3D printing was complete, I glued the two halves of the body together, then began inserting all the mechanical key switches I had ordered online, which the cheapest option at the time was 100 switches in total for about $27. Once the key switches were inserted, I soldered each into the matrix, carefully following the grid to ensure each key was wired into the correct column and row. I also used yellow wires for the columns and black wires for the rows to help differentiate the two. Which, as I went along, I ended up printing a few other parts to aid with the design, such as this conversion shroud, which has 20 holes in it for each column and row to be routed into before transitioning to stranded wires, which I used red and blue for the columns and green and black for the rows. Then I used a wire loom to contain all the stranded wires neatly going out from the keyboard body, but then I needed to add another part to help reduce the stress on the shroud, so I quickly glued this friction clamp in place for the bundle of wire to feed through and distribute some of the stress to the top beam. But following the bundled wire out from the body, it finally meets the breadboard where it can connect the columns and rows to the corresponding ports of the microcontroller. But then I needed my own custom connectors, which I easily did by soldering the stranded wires directly onto male header pins. Then for ease of plugging and unplugging from the breadboard, I 3D printed a sort of shroud to surround each connector and filled it with hot glued for rigidity. Then finally, I had completed assembling the main body of the keyboard and finished it off by plugging in each of the keycaps I had printed for it, which for a bit of fun and to test it before interfacing it with the microcontroller, I hooked all the columns up to 5 volts and hooked the rows to several LEDs and resistors and pressed each key one by one to make sure the connections were correct. With the key matrix itself figured out, next comes the greater part of the circuit on the breadboard with the microcontroller itself. In this design, I've dedicated ports 1 and 3 to be responsible for scanning over the columns of the key matrix, then port 0 is dedicated to scanning the rows. Notice that on each pin of port 0 connected to a row, there is also a 1 mega ohm pull-down resistor connected from the pin to ground. This pull-down resistor ensures that the state of the particular pin on port 0 is always low, or 0, and only in a high state when another high signal is applied to the pin, which occurs during a key press action, as described earlier when we went over the key matrix. While on the topic of port 0, I may as well quickly mention that port 0 is an open-drain bidirectional port without any internal pull-ups. Referencing a diagram from the MCS51 manual, we get an idea of what each pin of port 0 looks like internally. As you can see, the pin is connected between two transistors. The top transistor is only used when port 0 is used for addressing external memory, and thus is the only time an output to port 0 will provide a logical high, meaning that if you wanted to use port 0 as an output, you would need to provide it with an external pull-up resistor. The rest of the ports have internal pull-ups as stated in the datasheet, but I figured I should mention this small detail in the event you try things differently from my design. Then for port 2, I have selected the lowest 2 bits for interfacing with the actual PS/2 connector. Bit 0 of port 2 is used for data, while bit 1 of port 2 is used for the clock signal. I've also selected bit 3 for using as a caps lock LED, and the other LEDs you see connected to port 2 are used only to help with debugging, as you'll see in the code. As for resetting the microcontroller, power on reset can be accomplished by connecting a 1 microfarad capacitor between 5 volts and reset. This provides the active high reset pin with a momentary high pulse that is pulled to ground by an internal pull-down resistor once the capacitor reaches capacity. Then for the system clock, I'm using a 24 MHz crystal resonator that is tied to the crystal 1 and 2 pins, as well as to ground through two 30 picofarad parallel capacitors. Determining the value of these two capacitors is explained in my first 8051 timer video. So now with the design and build of the keyboard itself understood, let's go through the specifications of the PS/2 protocol and walk through how communication is done between the host and device and vice versa. Now when it came to finding information regarding the protocol, I didn't really have too much trouble, but there were some rather weakly documented areas of the protocol that most sources I found either didn't touch on or were somewhat conflicting or contradicting. Fortunately, it was not too difficult to find information on the actual communication streams. For instance, device-to-host communication occurs in the following manner. Each frame or packet consists of a single start bit that is always low, or 0. After follows the byte of data to send, that is 8 bits, which are sent least significant bit first. After the byte, then follows the parity bit, which is odd parity. Then finally the stop bit, which is always high or 1. This frame of 11 bits is then clocked into the host serially, and each bit is read by the host on the falling edge of the clock signal. The device is responsible for setting both the data and clock lines during device-to-host communication. When communication is complete, both the clock and data line should float in the high state. Additionally, the device should check the clock and data line to verify both are in a high state before attempting to send any information to the host. You'll see why in a moment. Host-to-device communication occurs a little differently. The same frame of 11 bits still exists, that is the start bit set low, the byte of data, the odd parity bit, and the stop bit set high. But there is one more bit that follows the stop bit, which is an acknowledgement bit always set low. These 12 bits are clocked into the device serially. This time, however, the device is responsible for controlling the clock signal, while the host is responsible for setting the data line. The host will set the data line during each falling edge of the clock signal generated by the device, and upon the rising edge of the signal, the device will read the value of the data line to acquire a single bit. This same action repeats until the stop bit is reached, where the host will then release the data line back to the device. The device will then acknowledge this action by setting data low and clocking one last time. Once this exchange is complete, the device should float both clock and data high. To help simplify this, the portions of each signal contained in red are controlled by the device. Additionally, whenever the host wishes to send a frame to the device, it will bring the clock line low for at least 100 microseconds, then bring the data line low before it releases the clock line. This is referred to as a request to send, and the device must respond to this request within 10 milliseconds. This is why the device must ensure both the clock and data lines are floating high before attempting to send information to the host. At this point, the rest of the protocol will be easier to explain alongside my code, so allow me to take you through my firmware and the process I went through in writing it. I'll be relying on information I already shared in 2 prior videos I made on some hardware features built into the 8051, specifically the timers and interrupts. If you don't know how these work, be sure to watch those videos for context. At the top of the file are 2 included headers, one for the 8052 symbols and one is the standard integer header, which I included so you may see how it can be used to declare an integer variable with a set size at compilation, which can be good practice for embedded applications. Then comes a couple definitions I've made. You'll see these used throughout the code, but most importantly, if you decide to try using a 12 MHz clock, then be sure to update the clock definition to reflect that change. Next is a version string starting at location 1FBF hex in the microcontroller's flash memory. This is done via 2 extended keywords shipped with SDCC, namely keyword code, which tells the compiler this variable is to be stored in ROM or code memory, and keyword at, which tells the compiler this variable is to reside at the specified address in memory. This string is not vital to the operation of the keyboard and only exists for my reference to what version a compiled binary is, and so I could show you how to use these SDCC keywords. Next is a 2-dimensional array of 4-byte integers that houses the key scan codes for each key present on the keyboard. This array is placed at some ROM location by the compiler due to the constant keyword, and each element is a 4-byte integer as specified by the 32-bit integer data type defined by the standard integer header file. These key scan codes are never to change, which is why they were placed in ROM. I've programmed each element or key code to include also the extension code if applicable, as well as the parity and stop bits for each code. To break down an example, the first code 0314 hex is for the left control key code. The least significant byte, 14 hex, is the actual key code itself, while the most significant byte, 03 hex, has bit 0 as the parity bit and has bit 1 as the stop bit. As far as calculating parity, because the parity is odd and the key code 14 hex contains an even amount of set bits, the parity bit becomes set. If the key code were to contain an odd amount of set bits, the parity bit would have been cleared, as is the case with the caps lock key code, for instance. As for the key codes with the extension code, the least significant byte is the key code, the middle byte is the parity and stop bit, and the most significant byte is the extension code. You'll soon see how each code, extension or not, is transmitted. Below the array are a couple different variables used throughout the code, but I'm going to come back to these in context as we run into them below, as they'll be easier to understand. So let's go ahead and skip right down to the main routine and walk through my firmware from there. The first thing done is to set up timer 2 to count 10 millisecond intervals and raise an interrupt upon each. You'll also notice throughout the code a few preprocessor directives that alter the code depending on whether a 12 or 24 MHz system clock is defined. This will ensure the timing remains accurate for either frequency. After this, I prepare the various ports of the 8051 for input and output operations. Even though the state of each port changes frequently throughout the code, it's a habit of mine to set the states of all pins before beginning any main loop. I then declare a couple variables, one of which is a 2D array for keeping track of a timestamp for each key on the keyboard. The others are counters and a buffer, which I declared outside the loop to save the microcontroller from having to initialize each repeatedly. After completing the init steps, the infinite while loop is entered. Within this main loop, there's essentially 3 paths of execution as indicated by the if-else statements. The first 2 paths have to do with the host either inhibiting communication entirely or initiating a request to send, while the third path is for normal key scanning. If communication is inhibited via the host pulling the clock line low, a 50 microsecond delay is entered, followed by exiting the if-else block and entering a second 50 microsecond delay, creating a combined delay of 100 microseconds, which is the minimum wait time required for the host to initiate a request to send. If, however, the host is requesting to send data to the device, the next iteration through the if-else block will check if the clock line was released by the host, and that the data line was pulled low by the host. In such a case, the interrupts are disabled for the time being before a call to the receive function is made. Entering the receive function, you'll see how I handled host-to-device communication. The first step is to wait until the clock line is high and the data line is low. Although this may already be the case when entering this function, it may not always be the case, thus it is best to verify it. This stage is also the first bit received, which is the start bit. We then enter the next while loop, responsible for receiving the actual data byte of 8 bits, as well as the parity bit and stop bit. This is done by lowering the clock line, waiting for a short period, then raising the clock line and reading the value of the data line that was set by the host. This value constitutes a single bit, and is shifted according to the current index value to ensure that the bit is placed in the correct position, which once in the correct position, the bit is ORed with the buffer variable to record it. At this point, with the start, data, parity, and stop bits all received, the only thing left is to send the acknowledgement bit back to the host, which the device does by setting the data line low and pulsing the clock one last time. At this point, all 12 bits in the host-to-device communication scheme have been sent, and the device may float the clock and data lines. The buffer variable containing the received data is then returned from this function. And while we haven't hit the function in the path of execution yet, allow me to also go over how the transmit function works. The transmit function handles the device to host communication. This function is used for both responding to host commands as well as to send actual key codes to the host. The first step is to back up the current value loaded into port 2. This step is only necessary because I am also using port 2 to control some LEDs. Next, the byte to transmit is copied into the variable last byte, which you'll later see why. Then a while loop is entered for handling the transmission of 11 bits, broken down to a start bit, the 8 data bits, the parity bit, and stop bit. The key code or argument is placed directly into port 2 and ORed with a set bit to keep the clock line high. The clock is then lowered, the key code shifted right 1 bit, then the clock is raised. I'd like to stress at this point that the timing of this transmission, at least to adhere to the PS/2 protocol specification, is critical. The clock frequency must fall within the range of 10 to 16.7 kHz according to multiple sources, and the frequency I've set up in my firmware is about 11.9 kHz. I had to do this with the help of my oscilloscope, and decided on creating an up and down time of about 42 microseconds for a total period of about 84 microseconds each clock cycle. Yet, as you may notice, the call to the delay microseconds function only specifies 16 microseconds for the downtime and 14 microseconds for the uptime. This is because creating a delay in microseconds becomes a bit tricky, as it actually takes a few microseconds to set up the timer. How many? Well, about 28 to 29 microseconds with a 24 MHz clock, which I determined by a call to the delay microseconds function with a parameter of 0. So admittedly, the delay microseconds function is slightly inaccurate, especially for values smaller than the setup time, but it is at least still consistent enough to produce a reliable reference for timing delays, working just fine with the PS/2 protocol, and can even create a perfect clock signal given some fine-tuning. Anyhow, returning to the main routine, the next step is to act accordingly on the command just received from the host. To do that, I wrote another function to follow the command, which is pass the buffer variable containing such. In the followCommand function, the passed command variable is first truncated to the least significant byte, as that byte is the actual data byte. A better practice might be to actually check the parity bit for accuracy, but I've decided to disregard it in this version of my firmware. After this is a switch statement containing a different case for each possible command sent by the host. I'll quickly go over just a few of the more pertinent commands and let you read through the rest on your own. The first is the setLEDs command, hex-ed. This command is sent by the host to change the state of the indicator LEDs for various lock keys, which on this keyboard design only the caps lock key and LED is present. An LED will turn on if its bit in the received argument is set, and turn off if its bit is cleared. Bit 2 is specific to caps lock, and the others are noted in a comment. Another command to look at is the read ID command, hex F2. This command instructs the keyboard to send its ID, which is AB83 hex. There are actually multiple different IDs for different designs, makes, and layouts of keyboards, but this ID is most common from what I read, and the design is very close to this keyboard's layout anyways. I'll link a source in the description if you'd like to read more about this. Another command is the set typematic delay command, hex F3. This command sets the repeat rate that a held key's key code is repeated, as well as the repeat delay that a key must be held down before its key code repeats. For this version of firmware, I've only coded in 4 different possible repeat rates. However, according to IBM's technical manual for the Personal System 2, there are about 32 different possible values for the repeat rate. Similarly, there are 4 possible values for the repeat delay, which I did implement exactly the same. As for the actual values I assign to each variable in the code, I'll fully explain them later in the code as they become relevant. There are many other commands aside from what I went over, such as for enabling and disabling the keyboard, resending the last byte transmitted, and even many which are ignored, but they're rather simple and I'll let you read through the rest on your own. So finally, we return back to the main routine from that function after handling the command received. At this point, interrupts are enabled once again and we continue into the next iteration of the infinite while loop. At this point, assuming that communication is not inhibited by the host, and that the host is not sending the command nor the keyboard responding to said command, and that the key matrix scanning is enabled and not disabled, the firmware proceeds to enter the path for key matrix scanning to detect and handle any key presses on the keyboard. Now recall the design of the key matrix. A 5-volt high signal is applied to any particular column by the microcontroller, and if a key switch is pressed on that column, the circuit is closed, allowing the microcontroller to detect that high signal via the active row. Translating this to code, the key located at column I and row J within the key matrix is pressed. This is precisely the premise of the 2 for loops in the code. The first for loop is for iterating over each bit of port 1 and the first 6 bits of port 3, as to set each of the 14 columns in the matrix high one at a time. The inner for loop is for iterating over the first 6 bits of port 0, as to check the state of each of the 6 rows in the matrix one at a time. With this in mind, for each column and row of the key matrix, the following paths of execution may be taken. First, the clock line is checked to determine if it is pulled low. If it is, the goto statement will immediately abort the key scanning and return execution to the beginning of the main loop so the microcontroller may monitor for further action to take as dictated by the host. This is another requirement of the PS/2 protocol, as the host inhibiting communication or raising a request to send must take priority over key scanning. Otherwise, the current key at coordinate ij of the key matrix is checked for an active high state, meaning that it is pressed. If so, then the key's timestamp that is stored in the 2D array key stamps is checked. If the key's timestamp is 0, then the key was not pressed before the current iteration, and therefore the key code must immediately be sent. This is done via the sendCode function, which is passed the respective key code and the number 1 as parameters to indicate that the key is being pressed. Entering the sendCode function, interrupts are first disabled to prevent interference with the transmission. Then the second parameter is checked, where 1 indicates the key is pressed and 0 indicates the key is released, because the PS/2 protocol sends the key code differently when it is released versus when it is pressed. When a key is pressed, the keyboard simply sends the key code by itself, except for key codes which are extended, where the keyboard will send the extension code before it sends the key code by itself. When a key is released, the keyboard will instead send a release code before it sends the corresponding key code. Similar to before, however, if the key code is extended, then the keyboard will first send the extension code, then the release code, and then the actual key code. Returning from the sendCode function back to where we were in main, after sending the key code, the key's timestamp is updated to the current value of the variable elapsed time. Which let's pause where we're at in the main routine for a moment to explain what the variable elapsed time represents. For that, we need to take a look at the function responsible for handling timer 2's interrupt. Recall that timer 2 is currently set to count an interval of 10 milliseconds before raising an interrupt and resetting. Upon each interrupt, the elapsed time variable is first incremented, then compared against the value 127. If elapsed time has become greater than 127, it is reset to 0. This is to prevent the most significant bit from being set, as any value greater than or equal to 128 will set that bit. This allows for using the most significant bit as a sort of flag, which you'll see in a moment. But the main takeaway to understand is that elapsed time represents how many 10 millisecond intervals have passed, and as such, for example, can represent a total of 1,270 milliseconds, or just above 1¼ seconds. With that known, let's continue where we left off in the main routine. The key's timestamp has just been set to the current value of elapsed time, which gives us a reference for when it was pressed. Now assume for a moment this first path of execution was not taken due to the key's timestamp being non-zero, as perhaps the first path occurred in a prior iteration. The next condition to check is how much time has passed since the key was pressed. This can be determined using a little bit of clever math. First, observe the two variables which represent a moment in time. Elapsed time represents the most recent moment, which is near present time. The key's timestamp stored in the key stamps array represents the moment that the key was pressed, presumably in the past. With that known, and verifying that elapsed time is greater than the key's timestamp, subtracting the key's timestamp from elapsed time will yield the total time that has passed since the key was pressed. This value can then be compared against the value set in repeat delay, which if the result of the subtraction is greater than the set repeat delay, this means the keyboard can begin to repeat the key code to the host. Recall also the values set in repeat delay we went over earlier, and assume for example that it is currently set as 25. Since both elapsed time and the key's timestamp represent intervals of 10 milliseconds, and if the result of the subtraction is indeed greater than the repeat delay, which is 25, this means that more than 250 milliseconds have passed, as 25 times 10 equals 250. The same concept applies to the other possible values of repeat delay, where the current value can be multiplied by 10 to determine how many milliseconds must pass before the delay is met. And since elapsed time can keep track of up to 1,270 milliseconds, the greatest repeat delay of 1,000 milliseconds can easily be kept track of. But what happens if elapsed time resets back to 0, but the key's timestamp is greater than 0? In this case, we must again be clever with math and understand that if the key's timestamp is greater than elapsed time, then we can subtract the key's timestamp from the max 7-bit value of 127 to acquire how much time passed beyond that moment, before elapsed time reset back to 0. We then simply add that result to elapsed time, which combines the time before the reset to 0 and the time passed after the reset to 0. The result can then be compared against repeat delay to determine if the delay had been met. Assuming either or of these conditions evaluates true, we proceed to set the most significant bit of the key's timestamp, which was actually a third condition I had glossed over. Remember how I mentioned that the most significant bit would be used as a flag? Here I am using the most significant bit to indicate that a pressed key has been held longer than a repeat delay, as this only ever needs to be determined once while a key is held. Recall that the repeat rate setting in a PS/2 keyboard represents how many times a second a key code is repeated, measured either by characters per second or hertz. Recall also the value set for repeat rate that we went over earlier, and assume, for example, that the repeat rate is currently set to 3. If we perform the modulus operation between elapsed time and repeat rate and verify the result is 0, this is equivalent to performing a division and checking that the remainder is 0. In other words, any division of a dividend by a divisor that has a remainder of 0 means that the divisor is a factor of the dividend. And if it happens that repeat rate is a factor of the current elapsed time, this means that an interval of time specified by the repeat rate has just been met. For example, assume elapsed time is currently 5. 5 divided by 3 equals 1, with a remainder of 2. As such, 3 is not a factor of 5, thus an even interval of 3 has not passed. If, however, elapsed time were 6, 6 divided by 3 equals 2, with a remainder of 0. As such, 3 is a factor of 6, thus an even interval of 3 has passed. And since elapsed time is measured in 10 millisecond intervals, the value in repeat rate represents the interval at which the key code should be sent, and to that end represents how many characters to send per second, since 1,000 divided by the repeat rate times 10, and with a repeat rate of 3, comes out to be 1,000 divided by 30, equals 33.3 characters per second. Then of course, every time the repeat rate interval is met, we can update the current key's timestamp with the current value of elapsed time while still preserving the set high bit as the repeating mode flag. And again, one other condition I glossed over was to ensure the key's timestamp does not equal the current value in elapsed time. This is to ensure the keyboard doesn't send multiple key codes at once when an interval of repeat delay occurs, because the microcontroller's instructions are occurring on the scale of microseconds, such that scanning over the entire key matrix can occur multiple times before even a single millisecond passes. And since the elapsed time variable only updates every 10 milliseconds, this condition could be checked tens or hundreds of times before elapsed time even changes. So now we've covered how to handle when a key is pressed, and the delays associated with repeating the key code after a set time and then every set interval thereafter. There is but one more path of execution that must be handled, and that is what to do when a key is no longer pressed but released. Assuming that the current key located at coordinate ij is not currently pressed, that is, no active high signals detected on its corresponding row, but its timestamp stored in the key stamps array is non-zero. This condition now means that the key was pressed during the last iteration, but has since been released. As such, the simple action of sending the release code can be done via a call to the sendCode function, passing the key code for the key and then 0 as parameters. After this function call returns, the key's timestamp in the key stamps array can be set to 0 to indicate the key is no longer pressed, but released. After all the rows of the key matrix at column I have been iterated through, we exit the inner for loop and another set of if-else statements are met. These statements ensure that the correct column is set high for the next iteration of the outer for loop, as the first 8 columns are connected to port 1 and the last 6 columns are connected to port 3, which the correct port pin is set by simply shifting the active bit of the column into the next bit, or by clearing port 1 and starting the process on port 3. And lastly, I have added a 100 microsecond delay between each iteration of the columns to fix one potential cause of key ghosting. As mentioned earlier, the diodes in the key matrix fix one ghosting bug. However, this ghosting bug I suspect is caused by parasitic capacitance, mainly because my circuit that is comprised of many overlapping wires and blobs of solder admittedly does not do so well to mitigate this phenomena. Plus, when I found the cause of this bug via my oscilloscope, it looked about like a capacitor discharging, taking just under 100 microseconds to completely discharge from a high to low state. For a version 2 of this keyboard, I will very likely investigate this issue a bit further, but for now this software fix works well enough and the delay isn't even noticeable. We are, after all, talking about millionths of a second, and I'd be surprised if you can somehow type keys that fast. Still, feel free to tweak this delay if you want to experiment with it. And finally, we've gone over the firmware in its entirety. After compiling the source code via SDCC and burning it into the microcontroller via the MiniPro software and an EEPROM programmer, we can plug the keyboard into the purple PS/2 port, which if you're plugging any PS/2 keyboard into a dedicated port on a motherboard, the port is generally not hot swappable, so make sure the computer is off before you plug in the keyboard. But with the keyboard plugged in, we can boot the computer. I'm using an older desktop PC I had lying around since it had the PS/2 port on it, but as you can see, the keyboard was recognized by the host and the host is receiving each key press just fine. And due to the design of the firmware allowing nth key rollover, commands such as select all, copy, and paste are all recognized as well. And of course, the caps lock key works as well, and if you recall the set LEDs command in the PS/2 protocol, the command is actually sent each time the caps lock key is pressed, which handles toggling the indicator LED for us. And if you go into the keyboard settings of your host, adjusting the typematic delay or rate will alter the repeat delay and repeat rate settings in the keyboard. Again, because I only implemented 4 different options for the rate, the slider only changes the values in each quarter section or so. But still, adjusting the sliders shows that the keyboard is responding to the command and adjusting its settings just fine. Also, the keyboard isn't limited to only Windows as you've seen, as it works great with various Linux distros and even macOS as well. Although it really shouldn't come as a surprise. If anything, it is a boost of confidence that the firmware is implementing the PS/2 protocol well enough. And although this is a PS/2 keyboard, you technically can even use it on a USB port with a proper converter, such as this PS/2 to USB converter. And actually, with this converter plugged into the keyboard first, you can hot plug the USB side into the host and avoid having a reboot for the keyboard to be recognized. So now, put that brand new PS/2 keyboard built from scratch to use. Now you can type up the endless flow of essays that professors just love throwing at you. Or you might even play a game or two in between. you know, if you need a break or maybe you're just procrastinating. Or you can cause a paradox and edit the very code currently running on the keyboard. Really, you can do anything with this keyboard just like any other, well, keyboard. In any case, have fun with this project. I do plan to continue working on this project as a whole and improve it, as there is a lot of room to do so. I'm actually working on a version 2 of this keyboard, as I originally made this project in early 2022. I won't reveal too much about it now, other than it will still largely utilize this firmware as a base, but instead be built on an actual PCB. But it is still a work in progress, plus I plan to make videos on some other projects of mine before then, so it won't be out for a while yet. And of course, any bugs I find or improvements made will be reflected in my GitHub repository for this project. You will also find documentation, schematics, and other files for this project uploaded there. That's all for this project. Thank you for watching, and until next we meet.